Today in this video, we're going to be starting our look into statistics, and we're going to be starting off just talking about statistical thinking, the thinking that goes with statistics. We're going to be covering some vocabulary, so if you do not have a pencil and paper for taking notes with you, pause this, go get it, because I'm going to be covering a lot of vocab today as well. And we're going to start right here. When we talk about statistics, we got to make a distinction between what's the data and what's the statistic. Data is the information gathered from observations or counting or measuring of responses, or it could be measuring of sizes. Statistics, though, is the science of collecting, organizing, analyzing, and interpreting data to make decisions based on data. So this is maybe a good way to sum that up. The data is the numbers. The statistics are what you do with them. What's the mean? What's the median? What's the mode? What are the implications of these? What's the graph that would go with this? There's two types of data sets. There's what's referred to as the population, which is the largest group possible. And then we've got samples, subsets of the population. Typically, population is difficult to get and expensive. So a lot of times when people are doing studies, they only do a sampling. But there's a lot of wrong ways to do a sampling. So for example, let's say that I was looking at this and I wanted to see the average height of all the females in a school. Well, I suppose I could walk out of my classroom door. The first high school girl I see, say, hey, can I take a tape measure and measure your height? And then claim that's the average height of all the girls in the high school. And I would hope that common sense is screaming at you going, well, no, that probably isn't right. I mean, I suppose there's a chance that it's right, and we'll be looking at probability. But there's a greater chance, I would argue, that it's not right. The chances that that one girl happened to be a good representation of the average height. So how do we take samples? Yes, maybe I don't want to take time to sample the height of every high school girl. How do I go about getting a sample that should represent the entire population in at least a decent manner? That being said, there probably would be some error involved, and we'll be looking at error later on in this class. Towards the end, we spend a lot of time actually talking about the error involved after we take a sampling, when we're making then conclusions, drawing conclusions from our sample. What's the error in the first place just from the way that I did that? Now, I could maybe do it this way. Instead of just that one, maybe I look at the entire room. Well, that's better than just one. Is that a good representation of the females in the school? Well, if you're in my classroom, and I know that we're distance learning right now, but if you're in my class, you're a senior. Is that still a good representation of the school? Well, I would argue no, even though I know that girls, for the most part, they're kind of done growing taller by the ages of 14, 15 years old. The entire school goes a lot younger than that. I could look at the entire school, and that's referred to as a census. It's a collection of data from every member of the population. And I'm sure you've heard this term when it comes to the United States Census, where the U.S. government once every 10 years tries to get information from every single person within the United States. The word census doesn't necessarily mean the U.S. Census. It just means it's a collection from every member of the population. Typically in this class, though, we'll just refer to something as the population and the smaller group, the sample. Thinking statistically, when you see numbers, there's an article here in a local newspaper a few years ago talking about the percent increase of basically the levy, which is the taxes, over the year prior. When you see numbers, you've got to stop and ask a bunch of questions about those numbers. Is this person trying to tell me something by putting these numbers here other than just the information? Are they implying something? In this case here, 3%, that doesn't sound so bad, 3% increase in taxes. But if you look at this entire chart that I started here, here's that right there. The grouping down here, if you add all that up, That's 32.1%. Now you're seeing a bigger picture. Well, wait a minute. Yeah, 3% didn't sound bad, but over the past 4 years from 2013 to 2017, that's quite an increase. That's almost 1/3 increase in taxes. And so sometimes by seeing more numbers, you're seeing a better picture. A question generally, then when you look at a number, would more numbers change my opinion? Sometimes you don't know. Even when you see more numbers, should I maybe see more numbers than that? Or is that a big enough sample? This sample only goes back to 2006. What if we went back to the year 2000? Would that change my opinion? That is something that you struggle with in statistics, is knowing how big of a sample should I actually be taking. There's a guy by the name of H.G. Wells. He was an author and a futurist. He liked to think about the future. He wrote the novel War of the Worlds, if you recall that. He said this: statistical thinking will one day be as necessary for efficient citizenship as the ability to read and write. And I think we're getting there. I think we are approaching that. If you've paid attention to current events in the last year when it comes to like big tech companies, how they're data mining us every time you use Google, every time you use Facebook, every time you use any of the social media, they're gathering data off of you. They're applying those statistical averages to manipulate you, is what the argument is becoming. Are they manipulating us? I would argue, yes, they are. There's been cited cases where of known manipulation, even cases where it's been documented where companies are experimenting on how much manipulation they can get away with. So I do think it's true. But when you're looking at just numbers, looking at the statistics, here's the things that you need to consider. What's the context of the data? What's the source of the data? What's the sampling method? In other words, what's the method that they collected to give this statistic? I gave the example of measuring one high school student and claiming that was the average height. That's a horrible sampling method, absolutely horrible, that would be thrown out by anybody that knows anything about gathering statistics. But you should be asking those questions when you see numbers, when you see averages thrown out, or mean. Typically in statistics we use the term mean. Medians, modes, standard deviations, variations, things, I know some of those terms you're not even familiar with yet. We will be by the end of the class. But you should be asking, hey, how did they get them numbers? What was the method that they used to get those numbers? Where did they get those numbers? Is this somehow going to be misleading? Did they draw a logical conclusion with what the numbers came out to be? And are the applications that they're telling us we should apply, are those actually practical applications, again, from what the study turned out to be? A couple of quotes here. We should never rely on blind acceptance of mathematical calculations. Another one. In learning to think statistically, common sense and practical considerations are typically much, not just a little, much more important than implementation of cookbook formulas and calculations. Now, you might be reading that going, I don't think this guy likes math. I don't think this guy likes statistics. Throw out the calculations, throw out the formulas. Let's make sure we're focusing on common sense and practical considerations. The reality is, this guy here that said both quotes right here, this is the author of your statistics book. Triola is the author. If you check out your statistics textbook, you'll notice the author's name is Triola. He said that. So anybody that's done any work studying statistics will tell you that you've got to use a lot of common sense, a lot of practical considerations when you're looking at this stuff. Don't just read numbers blindly that are shown to you in whatever form of media given and go, well, that just must be true. Looking at data, got some numbers here. When you look at data, you should be asking, do we have enough information to analyze? Well, maybe, like in this case, I suppose we could find an average, a mean, or something. We could do some analyzing there. Do we know the context? What could the numbers represent? Do we know the source? Is it a reliable source, or does somebody just make them up? There's an old joke, 57.2% of all statistics are made up on the spot. Do we know the sampling method? Is it covering the entire population? Was it a random sample, or did they just grab whatever it is they're studying here, the easiest things they had to get to, and puked out the numbers? Was it a large enough sample? What are the conclusions? And of course, at this point, we have no conclusions to this. But when you're looking at a study and they start to draw conclusions, were they clear conclusions? Do they discuss correlation or causation? In statistics, we can discuss correlation. We don't generally discuss causation, things that cause other things to happen. We generally are just looking at, well, these seems like these things go together. We can apply our conclusions to different populations, or excuse me, can we apply our conclusions to a different population? And are there any practical applications? So here, what if I told you that the study, the numbers you're looking at here, has to do with an old saying from freshman year of college that freshmen tend to put on about 15 pounds, or in this case, it actually was done in kilograms, in a year. Would this change your answer at all? So here's the actual study. The study was titled Changes in Body Weight and Fat Mass of Men and Women in the First Year of College, a study of the freshman 15 by Hoffman, I'm not even going to try to pronounce that, Quick, and Lee. So 4 people worked on this study. And this was for the Journal of American College Health. So this is a journaled article. Journaled articles are always given to scrutiny, which means people look at them and go, did you use the correct methodology? Did you draw the right conclusions? Did you draw the right practical applications, and so on and so forth? That's why people publish in journals, is so that others can scrutinize. In this case, the X and Y variables refer to volunteers' weights, again in kilograms, not pounds, but in kilograms, in September, so I believe September was X. And again, for those who returned in April, that would be the Y. Of the original 217 volunteers, only 67 were measured again in April. The sample was not random and may have introduced self-selection bias by the publishers. There's a bunch of bad stuff in that paragraph there that I want you to start to learn to look at. Here's some of the bad stuff. Notice we started out with 217 volunteers. That's going to be part of down here. There was a statement made that it was not random. If people are volunteering to be part of the study, it's not random. And in statistics, it's really, really, really important to, if it's going to have any reliability at all, that it be random. And we're going to be covering how do you randomize. Well, there's lots of ways you can randomize. But if there's a human being making the decision of whether that data point is included or not, it is not random. So obviously volunteers are choosing. Now, not only did they have volunteers choose, so that first mistake, already you're kind of going, not a great study. But in this study, they didn't even require the 217 to come back. They said, come back if you feel like it in April. Okay, so it wasn't random. It was volunteer. It didn't even include the original sample size. It lost, about 3/4 of the people, it would appear, didn't even come back, which introduced, because of that, what's called a self-selection bias. People select themselves based off whether they want to be or not. I mean, just think about it. If you were back here, and we'll put this in pounds. Let's say you went off to college and you weighed, let's take a guy who weighs 170 pounds. And by April, he's weighing maybe 230 pounds. Woofta. He likes his carbs. Would you really want to go back and tell people, hey, I've gained a ton of weight this year? No. So that's the self-selection bias. You're already introducing, by the fact that people are volunteering and only have to come back if they want to, a ton of error in this particular study. It is a published study. In fact, that's a decent journal right there, but it's still, they had their methodology for collecting their data. A lot of holes in it, we'll put it that way. With the freshmen that did return, analysis did show gain in weight, but the weight gained by the small returning group was less than 15 pounds, so they concluded that the freshman 15 was a myth. Notice they drew a conclusion here. Because of their faulty sampling methods, most likely this is a faulty conclusion. And that's how you got to see numbers. You know, to just say, hey, these people did a study, and in their study they said the freshman 15 was false. It might be false. I don't know if it is or not. What I do know is my opinion is not going to be based off of this study, because of this study was done horribly. If somebody came along and did a randomized, not volunteer study, it would carry a lot more weight with whatever conclusion they happen to draw. So I've pretty much already covered this, but I'm just throwing out the kinds of stuff I talked about. Volunteers, that was an issue. The sample size, actually they didn't have a bad sample size, but the problem is they lost about a fourth of it coming back. Correlation causation, now that's something that we really can't address. Does being in college your freshman year correlate with gaining weight? Possibly. Does it cause you to gain weight? Possibly, but in statistics we don't generally talk about causation. That's taken up someplace else. Is there a connection between the numbers? That's what correlation is. Correlation just says, hey, is there some connection between the numbers? And again, we'll be looking at that later on. Let's look at another one here. I saw this in a textbook, and I'm not going to necessarily go through what textbook it was here. And I do apologize, my picture's kind of, I got a bad glare here at the top. And what that says is transportation fatalities. So we've got the occurrence to people in the United States. So this is in a year. In an average year, this is how many people die in car crashes. This is how many people die from slipping, tripping, or stumbling. This is how many are struck by lightning. This is how many are killed by lightning. And again, this is just in the United States. Got a funny one here. You're bitten by a squirrel in New York City in a year. That's how many people get bit by a squirrel. Killed by a dog bite. Killed by a snake bite. Bit by a shark. Killed by a shark. What point do you think the author is trying to make with this picture? Well, you might not know. And again, there's no context here. I haven't given you the context. If I give you the context, then we can talk about it. The context on this, in this case, was trying to make the case that the great white shark is misunderstood, and I would argue implying that the great white shark is much safer. At least I believe that's what he's trying to do with the data, imply that the great white shark is much safer than, say, a squirrel. Okay, or much safer than a dog. If you think about it, though, some things should jump out at you, and maybe they're not, because this is really your first unit into statistics. Thinking critically about these kinds of things doesn't necessarily come natural, which is probably why I'm a little bit of a cynical person, because I see this stuff and I know that people can be manipulated by the fact that it is easy to show numbers and manipulate people. You look on here, it's like, well, killed by a shark, only, no pun intended here, but that's about a half a person a year, okay? It's 0.4 of a person a year, so that's a pretty small number compared to, you know, killed by a snake bite or killed by a dog bite. But I would argue this. Living in Minnesota, I believe that there's been no shark bites in the state of Minnesota ever on record. Have there been dog bites? Sure. Snake bites? There's a few rattlesnakes down in the southeastern part of the state, so there's probably been a few people killed over the last 100 years or so by snake bites, but not many. Killed by lightning? Yes, there's been people killed by lightning in the state of Minnesota, but we've never had a shark kill anybody in the state of Minnesota. So maybe the sharks in Minnesota are safe, which of course is a little bit of cynicism on my part, because of course we don't have any sharks in Minnesota. Which I want you to then think about. Do we have lightning in the entire United States? Yes. Do we have dogs in the entire United States? Yes. Snakes? Well, we have them for sure south of Minnesota. Do we have things to stumble in the United States? Everywhere in the United States? Sure. And cars? Are there cars everywhere? Sure. Are there sharks everywhere? No. Not even close. Okay, it just on the bordering edge of the United States. Of course, we got the East Coast, we got the West Coast. I don't know how much swimming in the oceans people do up in Alaska. I'm guessing not a lot. Obviously, in Hawaii, there's a lot of surfing. Hawaii, California, Florida, those tend to be the places where these happen, which percentage-wise is a percentage of just where people live and where people are, is smaller. Not to mention that the people that are killed are doing recreational things. They're swimming, they're surfing, something like that. How much of a person's life, what percentage of a person's life is done doing recreational things? You really start to think about it. This is a ridiculous chart because the sheer chances based off of location and probably, so take the slipping and falling or driving a car. Well, we drive cars every single day, multiple times a day. We go up and down stairs or walk on slippery surfaces a lot. Of course, this is going to be higher because of our probability of being in those situations is much, much, much higher. I've only personally swam in the ocean twice in my life, but I have been in a car pretty much every single day of my life. So I would expect these to be quite a bit different. And this is what I mean by critical thinking. When you see numbers, people will look at that and go, oh yes, those poor, poor sharks. We need to try and protect those. And I'm really not against sharks. Please don't take it. I'm against this data set. This data set is horrible because I know that there's an argument. I read the rest of the page. They were arguing that based off of this data set, that great white sharks are greatly misunderstood, and they implied that they were a safe creature. I tell you what, I would not want to jump into the ocean where there was a large gathering of great white sharks. I know they don't school, but they do gather sometimes for feeding. I wouldn't want to get caught in the water. I don't care how safe the author of this might think they are. All right, let's move on. In statistics, we have two branches, and you'll definitely notice this as we go through this class. We have the descriptive statistics. In descriptive statistics, we look at organizing our numbers, putting together what are called frequency distributions. We summarize our numbers. We summarize our statistics. We display, that's graphing. We make graphs of our data. We make graphs of our statistics. Inferential basically is going to be the second half of the class. Literally, you could just about split this up into the first half of the class and the second half of the class. The first half, not nearly as much calculation goes into it. The second half, tons and tons of calculations go into this. But the idea is we are using to draw conclusions. We have to include probability on doing that. What's the probability of this conclusion being done correctly? And we do this with what are called confidence intervals and significance tests. Let me give you a quick example here of what this is sort of talking about. Let's say that we've got a manufacturer of tires and they've been having some quality control issues lately. A lot of tires blowing out on the highway, so they make some changes in their manufacturing process. And then they start to gather data. And after a while, let's say that their safety used to be about this much, and now it's more. Is it more enough to call safer, or is it could be that because of the samples taken were random samples, could the variation only be because of randomness when collecting those samples? So we test to see how significant is the change. Is it significant enough to overcome the randomness of just gathering samples? And confidence intervals are actually related to that idea. Again, this is kind of the first half of what we're doing, making graphs, numerical summaries, finding ways to summarize what we're looking at. And these are the two branches of statistics. Again, as we go through, we have populations and we have samples. When the statistic comes from a population, we call it a parameter. When the statistic comes from a sample, when the calculation comes from a sample, we call it a statistic. Typically, the way this works, like with the tire example I just gave, we want to know how safe the tires are. We've got an entire population. So we pull out some random samples of people or tires or whatever you're talking about, and we've got to find a way to randomly make this so that everything that's being pulled out has just as much chance as any other thing that you're pulling out of the population to sample, otherwise it's not completely random. We collect our data from our sample. We go through the process of calculating our statistics, means, modes, things like that. And then we apply what we've learned back into the realm of the population. So then we imply what we think then is true about the parameter in the population. Again, if we're talking about a mean, we could take the population and find the mean, the average, and go directly to it. But again, sampling populations is difficult and very expensive typically, so sampling is more preferred as long as the sampling is done correctly. But to do this process, we have to know what type of data we're collecting. Okay, so that's our next thing. We have different kinds of data. Here's our different kinds of data. We have categorical, qualitative, describing a quality, and attributive, describing an attribute. Labels. Any data that is not numeric is qualitative. Say blue eyes, that's describing a quality. Numbers used more as labels are also qualitative and wouldn't make sense to add or subtract them. So like eye color. A jersey number. Taking Michael Jordan's jersey number and say subtracting that from Shaquille O'Neal's jersey number, yes, I would get a number, but the context of it would mean it's a worthless calculation. It doesn't mean anything, so it doesn't do any good. Then we have what are called quantitative. So there's categorical data, also called qualitative data. Once in a great while, I've seen it called attributive data, but typically your textbook's going to refer to them as one of these, and more often than not, I'm going to refer to it as qualitative. Data that just describes a quality. And then there's quantitative data that's based off of some sort of either counting or measuring. I've counted how many people have blue eyes, or I have measured the length of the last 10 walleyes that I caught. When you have these, you can compare them, you can add them, you could subtract, and they might actually mean something. Obviously, I could find the average of the lengths of fish, and then I could add or subtract different fish to that average. Okay, decibels. Okay, there's something I can measure how loud sound is. We measure sound in decibels. Weight, we can measure. 6 foot 3 inches tall, we can measure height. We can count, like I said, we could count how many people have blue eyes in a particular sample. Things like that, so we can measure and we can count. That's quantitative. Qualitative is just describing a quality. So a little practice here. A phone number and a phone book. Is it qualitative or quantitative? I would argue that even though there's a bunch of numbers, that's a qualitative number. A list of teams in the NFL. a list of teams in the NFL, is that qualitative or quantitative? Well, it's labels. You've got the Vikings, you've got the Packers, things like that. So that's qualitative. It's describing a label. The height of all students in a particular class. Well, that's quantitative. I can measure that. Social security numbers. It's like phone numbers. Yes, there's a lot of numbers, but, well, this one's actually a little bit weird because this could go either way. It's describing a person, even though I do know that they are assigned in order of when you were born. So you could, in this case, subtract and it would actually mean something. This is one where I would also accept an argument of, well, it's qualitative. I'm going to tell you right now that when you take my tests, there's a lot of these things that can be a little bit subjective. And when they are, I am more than open to having you come give me your logical reason as to why you think it is or isn't. So this would be one of those. Social security numbers could kind of go either way. Populations of the largest cities in Minnesota, okay, that should be quantitative. We can count how many people there are. We could subtract. It makes sense. Top 5 selling cars of 2010, I would say that is quantitative. We can count how many sold. Shoe sizes, that's a measurement. We can do that as well. When we talk about data, there's also what are called the levels, 4 levels of data. The levels have to do with when we do calculations with these, at what level does it actually make sense? We don't do much with the nominal level. Nominal level is, again, names, labels, categories. We can't even arrange them where in a case that makes sense. Say from high to low. Arrangement doesn't even really mean anything. And obviously that's qualitative. An example, a Democrat or a Republican. It's a label, so it's nominal. We don't say that, well, this Democrat is twice as much of a Democrat as that Democrat. Well, we might talk stupid saying things like that, but in reality, it doesn't make any sense to actually make that statement. The next level is what's called ordinal. Things can be ordered, but differences are meaningless. And this one could be qualitative or it might be quantitative. Some examples of this would be first, second, third place of a team. Okay, you got a first place team, you got a second place team. I can order them. Obviously, first place won or is better, however you want to say that. Second place is not as good. But if I subtract, say I take second place minus first place, 2 minus 1, well, that gives me 1. Does that make any sense at all in this context? No. So making a subtraction of the numbers doesn't mean anything. That's the ordinal level. So I can order them, but subtraction doesn't mean anything. Letter grades. That's a good example. I can order them, but A minus B doesn't really mean anything. Now, I know people can argue, well, what about 85% minus 80%? That's different to me, though, because now you're talking about the numbers. If I'm talking about specifically letter grades, subtraction doesn't mean anything, so I would say that's ordinal. The next level is called interval. It makes sense to add or subtract, but does not have a natural zero, and these are qualitative. Now, this spring, I'm going to be asking you, you're going to be doing a big project, a final project. I'm going to be asking that when you do your study, that it be at least to the interval level. I want it to be quantitative, something you can measure or you can count in a situation where it may not have a natural zero, but adding and subtracting does at least make sense. So let me give you some examples here. Temperature is a great one. Does temperature have a zero? Of course it does. Does it have a natural zero? No, it does not, at least not in the Fahrenheit scale. In the Celsius scale and in the Kelvin scale, it does. Now, what I mean by that is 0 degrees. Is that the absence of heat? I mean, there's like no heat left at 0 degrees Fahrenheit. No, because we know we can continue to get colder. So this is not a natural zero. See, a natural zero means that there's nothing of it left. Well, what is temperature? Temperature is a measure of the amount of heat in something. Well, 0 degrees Fahrenheit doesn't mean there's no heat left. Otherwise, it wouldn't be able to get any colder. So this is an interval. That being said, the Kelvin scale is not interval because 0 actually does mean the absence of heat. So don't just think, well, temperature is interval. It depends on what scale you're talking about. The Fahrenheit is interval. The Kelvin is not. The next one that Kelvin would fall under would be a ratio, the level of ratio. Has an inherent 0. So the 0 means none of it, or nothing. Okay, and we can say that one is a multiple, that's the term ratio. One's a multiple of another. And of course, it's going to be quantitative kind of that. So this is a little confusing because we have quantitative and qualitative, and then within that, we also have these, which could be up to here, either one. Well, I shouldn't say it. The first one can only be qualitative. The second one is either. The third one is quantitative, and the fourth one is quantitative. An example here, it says money. Okay, $0 is $0. I can't buy anything because I got nothing. This is in a ratio of 4 to 5. Okay, if one person has $40 and one person has $50, there's a ratio there of 4 to 5 of between a comparison of the two. Grades as a percentage, 0 would mean something. 0 would mean nothing. They didn't do anything. They didn't turn anything in. They didn't accomplish anything. But I can also set up ratios here. So this would be a ratio level. Again, when it comes to the end of the semester, I know we're right at the very, very beginning, but this is a building class. Everything's going to build to the end. So from day one, we got to keep track of stuff. At the end, I'm going to ask you to do a study that is going to be either interval or ratio level. It can't be one of the other. I'm going to ask you which one it's at. I'll be asking you in your final project to tell me whether it's qualitative or quantitative and at what level of data you're using. So let's practice a little bit. Top 5 TV programs. What do you think? Nominal, ordinal, interval, or ratio? Top 5 TV programs. Would 0 mean anything? A lot of times you go back down to the 0, a 0 rating. Well, that might mean something. For sure, I can have labels. Can I be ordered? Well, yeah, I can order these things. Does subtracting mean anything? Maybe. So you might start to fall into this, and this is that subjective thing again. I honestly think, depending on your thinking, you can argue a couple of good ones. So I would put it in here. A collection of phone numbers. Pretty much phone numbers are labels. And so you're going to be stuck with nominal. Body temperature of an athlete. Well, are you taking it in Fahrenheit or are you taking it in Kelvin? Because if it's Fahrenheit, you're going to be here. If it's Kelvin, you could be here. Heart rate of an athlete. You know, a 0 heart rate does mean something. It means you're dead. And so I would argue that that's going to be a ratio. Temperatures, again, you're talking about Fahrenheit, you're talking about Kelvin. So it's kind of a bad question. So it's a little bit subjective. Types of music played by, so like country versus Christian versus pop versus rock. Those are just labels. I'm going way back to nominal. I'm saying that's a nominal thing. Okay, hopefully you're getting the idea here. Quantitative can also be separated into what's called discrete data. And, well, sorry, I thought I was going to get to the next one first. We'll do discrete first. It can only take on a finite or countable numbers, countable being like 1, 2, 3, 4, 5, things like that. They're whole numbers. Fractions don't mean anything in this case. If we take it apart, it doesn't make a lot of sense. Like parking spots is discrete. You can count the parking spots, 1, 2, 3. You can't have a fraction of a parking spot. It doesn't work to have a fraction of the parking spot. So parking spots are discrete. Continuous is the other. Continuous, in this case, it is an uncountable number of possible outcomes in each given interval, which I know doesn't make a ton of sense to you, but a big application of this has to do with time or weight. Okay, so take a child growing between, say, 23 pounds and 24 pounds. There was literally an infinite number of weights in between those two. This is what I would say. Write down an example that for to be continuous, most of the things we're talking about are time and weight. Even though we might be able to count seconds, there's an infinite number of moments between each second. So time is continuous, weight is continuous, length is continuous. There's an infinite number of numbers between the numbers when you go between, say, 10 and 11 inches. Some stuff's discrete, some stuff's continuous. It's actually easier to think about what these are than what these are. Basically, the idea here is you're counting one of them, two of them, three of them, four of them, so on and so forth. Or none of them. That would be the whole numbers start at 0. I get to some examples here. Length of a wall angle, like, well, that's got to be continuous. The number of people that prefer chocolate to caramel, well, that's going to be discrete. You can't have a half a person. You might have a statistic of a half a person because you're averaging, but when you're counting, you can't have a half a person. Okay. I'm going to have this in Schoology. This is a nice little breakdown for data. You should go there and you should print this off. Otherwise, I'll have these available in class. Kind of just organizing everything we just talked about and the different qualitative, quantitative. Within quantitative, there's discrete, there's continuous. Then it gets a little bit messy here. Which things can be interval, which things are ratio. Over here, there's ordinal, there's nominal. Those are quality things. Of course, some ordinal things can be quantitative. And then there's binary. I didn't even mention this. It's really just two options. Yes, no, pass, fail. That falls under qualitative. Binary, we actually do quite a bit with the binary distribution, which I know doesn't mean anything to you right now, but it will in the future. All right, a couple of notes here. Here's some problems to take a look at. The readings, I'm asking you to do a reading right here. I do test on these readings. Don't blow them off. Open your textbook, do the readings. Every test, I will have questions based off of the reading. I do have an expectation that you're going to read in this class, not just follow just the lectures. I expect that you'll go over the material in the lecture and go over the material in your textbook. Here's some problems to practice. There are some examples given that go with some of these problems that I did not get to. So that's what I mean by expect you to read. That's it. Have a good day.